section, guys. Carboxylic acids. Carboxylic acids have this kind of structure to them. They contain what we call the carboxyl group. The carboxyl group is this C double bond OOH group here. So this is your carboxyl group here kind of thing. And once again, we're going to have a long chain of carbons attached to that probably. Okay. Sometimes we ask, does that carbon count, that carboxyl group? And the answer is yes. Technically, the long chain of carbons is actually this right here. Okay. But the carboxyl group is basically that COOH group. That carbon still counts in the long chain. I'll show you in a second here. Okay. When we go to number these carbons, carbon 1 is this one right here. Carbon 1 is always that one. Okay. Always, always. So we have to keep that in mind when we're going to number these carbons. If you're going to name and draw carboxylic acids, the parent chain has to contain the carboxyl carbon, which is always C1, which I just talked to you about just now. To name carboxylic acids, we're going to drop the E. So for example, if it was butane, 4 carbons in a row, we're going to take off the E, and we're going to put oic acid on, because it is an acid. So butane, if it had the double bond O with the OH, it would be called butanoic acid. Okay. Drop the E and replace it with the oic acid. Branches are numbered and named as usual, but remember carbon 1 is the one on the double bond O, OH, that's carbon 1. So here we go. Butanoic acid, first one. Normally when you write these, you do them like this. Okay. Butanoic acid, of course, 4 carbons, but. Okay. Double bond O, OH looks like that. Okay. That's the carboxylic acid, basically version of butane, butanoic acid, and of course just fill in the rest with hydrogens. Now, some of you guys may want to write this backwards, so you want to put the double bond O on the left-hand side kind of thing. I'm going to tell you right now, more often than not, you're going to see it like this. I'd rather you do it like this because it's going to help with the reaction part later. However, you could see, this here, but remember, this will be double bond O. This will be OH like so. Okay? The C has to bond to the O, which bonds to the H, right? You can't have C, H, and then another O there. There's no room for it, right? So it has to look like that. I don't care, honestly, which way you write it. I'm going to tell you this is easier, and this is going to be better for you down the road. Okay? But it's up to you, ultimately. So this is butanoic acid here. What's the next one here? Once again, where do you start with these? You start at the end, as always. Pentanoic acid. That tells me I need 5 carbons. Pentanoic. 5 carbons. Double bond O, OH, pentanoic acid. And what else do I have here? I have 4 bromo, 2 methyl. Don't forget. Carbon 1, 2, 3, 4, 5, yes? So 2 bromo, I said. Is that right? 4 bromo? 4 bromo. 4 bromo, 2 methyl. Let me get my... Yeah, 2 methyl, okay? So that's what you need to have for that one. This is carbon 1 all the time. This would be 2, sorry, no, that's 1 there. Let's just get rid of that. Okay, this would be what, 2 there, 1 there, and 3 there. Okay? Good? These ones are actually kind of easy, right? Because, I mean, they're basically what we've done before, except with the oic acid part at the end. Let's look at the next one here. Next one says what? Once again, where do you start? You start at the end, right? Propanoic acid. Okay, that's 3 carbons in a row. Propanoic acid looks like that. 2,3-diphenyl. Don't forget this is a 1 here, so the 2 has to go here. 2 and 3. Fill in H2 there, 1 there. Don't forget this carbon has 4. 1, 2, 3, 4 around it, so that one's good. Okay? Yes, good? Questions, anyone? Yeah. Okay. Naming. Once again, find longest carbon chain. In this case, you notice it's got a double bond OH, so I got to include that kind of thing, right? It's got to be part of it. Longest carbon chain is probably this one right here. And yes, you probably should include that as well, of course. You'll see that main feature, that carboxyl group, that has to be the key here. That is the main thing. So this carbon does count, guys. Okay, so this is carbon 1, 2, 3, 4, 5. That's pent. It's got that carboxyl group on there, so it's pentanoic acid. There is a break there. That is not all one word, of course. So it is pentanoic acid. Okay. And don't forget, of course, on 1, 2, 3, there's 2 methyl groups here. So 3,3-dimethyl pentanoic acid, all one word. Well, 3,3-dimethyl pentanoic, all one word, acid. Okay? Obviously, these are acids, yes. Yeah. The oic part, yes. The double bond OH, yeah. Yeah, basically that's the name of these. So it's pentanoic. It's a carboxylic acid is what it's called. That's the group. No. No. I always try to put them on the right-hand side because it works out better that way. But you don't have to. This one here, once again, longest carbon chain, guys, probably this one right here. Okay. 1, 2, 3, 4, 5, 6. 6 carbons with the double bond there, so that's hexanoic acid. Right, carboxylic acid is what that's called. And on the 1, 2, 3, I have this add-on group here, so that's 3-ethyl hexanoic acid, all one word, except for, of course, there's a break between the acid and the all one word. 3-ethyl hexanoic acid. Okay, good. Moving on. Yeah. Okay, those are probably, honestly, those are probably the easy ones, okay? Out of those 2 we're going to do today anyway. Physical properties of carboxylic acid, so a little cue card stuff here probably for this. The C double bond OH, first of all, when you think about that, double bond OH, very polar end to that molecule. It's got hydrogen bonding as well, so when you think about hydrogen bonding, you think about high melting boiling points. When you think about double bond OH, very polar end, you think about very soluble in water. So that tends to be the case here. To form hydrogen bonds with one another, resulting in much higher boiling points. You know, here's an example. These are kind of some of the ones that we've compared to, and this is a good comparison. You should understand this. Butane is nonpolar, London forces. Probably lower melting boiling points, right? Look, 0.5, negative 0.5, but let's call it 0, okay? Just there. Alcohol, butane 1-ol is what we did yesterday. That's an alcohol. That's got an OH group attached to it. So the only difference between butane and butane 1-ol, of course, is the OH group, right? I mean, that's the only difference. First of all, OH, hydrogen bonding, so very high melting boiling points. And polar as well, right? So butane 1-ol, look at the difference between these two just by adding an OH on there. Quite high hydrogen bonding, right? 117, right? 0.2 degrees Celsius. That's a big difference. 0 and 117 Celsius. That's their boiling points in this case. A little bit more polar and hydrogen bondings, butanoic acid, double bond OH, more polar end to it, 165.5. So you'd expect this trend to happen with pretty much most of alkanes versus alcohols versus carboxylic acids. Okay, that usually tends to be the trend, assuming everything else is equal, of course, right? So I'd expect the same kind of trend with methane, methanol, and methanoic acid. Same kind of trend, okay? Things like that, okay? The polarity of the COOH causes the short chain, 1 to 4 carbons, very soluble in water. What happens though, as you get larger and larger, so you got 1 to 4 carbons, very polar, very soluble in water. As soon as you start lengthening out the chain, the non-polar characteristics of the CH3, CH2, 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 and then the C double bond OOH, that non-polar stuff starts to take over a little bit more and becomes less and less polar. Same with alcohols, by the way. Okay, alcohols and these are very, very similar. So what happens is when you get to 5 to 9 carbons kind of thing, so kind of somewhere in the middle there, it becomes slightly soluble in water, so they tend to decrease in solubility. And then once you get above 10, you know, it basically becomes insoluble in water. So once you get very, very long chains of carbons, that polarness tends to wear out kind of thing, and they become insoluble in water. So these are 2 points here that you'll also want to know along with the first page there. So, and that's the same for alcohols as well. 1 to 4 carbons for alcohols tend to be very soluble in water, very, you know, very good. 4 to 9 or 5 to 9, they kind of start to wear out a little bit. They become a little bit more slightly soluble, and then higher ones tend to be insoluble. Okay. Carboxylic acids are, well, as the name implies, they are acids. They are weak acids. Okay. They will turn litmus paper red. They will conduct electricity because they will ionize. Even though they're molecular, of course, they go through the process of ionization slightly, okay, because they are weak. Esters. Esters are a little bit more complicated. Esters kind of look like this here. So what you'll notice is that carboxylic group, or that, sorry, not that carboxyl group, is in the middle of the chain now. It's not at the end anymore. So it's not as simple as starting here and working your way left, or starting here and working your way right. Now we have it in the middle somewhere. And you're going to have 2 chains, long chain here, of course, and you're going to have a long chain out this way perhaps. And with those chains, you can add on stuff to those chains as well. So it can become quite long to describe that. Esters contain a carboxyl group somewhere in the middle of those long carbon chains. So you basically got a long carbon chain here, a long carbon chain there, and that's not on the end anymore. Okay. Having said that, here's how it works. As always, this is still carbon 1 here. Okay, no matter what. So you start in the middle, and you're going to go this way, and you start in the middle, and you're going to go that way. So technically, carbon 1 over here would be over there. You got 2 different parts to this compound. So you're going to have 2 different carbon number 1s, and I'll show you how to name those eventually here. Okay? But you got to start in the middle and kind of work out, kind of from both sides. Okay? Esters are formed by a reaction. Believe it or not, this type of reaction is called esterification, because you're making esters. So during an esterification reaction, which is something we're going to talk about a little bit more coming up here, they're made from a carboxylic acid and an alcohol. And you know what those 2 look like now. So the carboxylic acid, of course, which we just finished talking about, looks like this here. Long carbon chain here, right? And you got your double bond OOH. Okay? Alcohols also have a long carbon chain usually, with an OH added onto here. That's what makes it the alcohol, right? So you got your long carbon chain here, and you got your OH. Okay? How it works is this, and this can get pretty confusing when we get to the reaction part. We're going to just keep it really simple today. But how it works is this. In an esterification reaction, you take a carboxylic acid and an alcohol, okay, and you basically mix them together. And what happens is the H from the alcohol comes off, and the OH from the carboxylic acid comes off. And I used the analogy, and then people looked at me in the first class, but I'll use it again anyway because I don't care. You guys know Price is Right? Yeah, you know what I'm talking about, Bob Barker, right? Price is Wrong. No, won't say that. Happy Gilmore. You know that game where you gotta, there's 5 numbers and you pick out the one in the middle. It's called squeeze play. You pick it out and it does this, and it actually makes that sound. My voice is a little shot there. Squeaky, and it squeakies together. You know what I'm talking about? And you pull out the one in the middle and it goes squeaky together. That's what this is. Okay. You take out the H and the OH, the H from the alcohol, the OH from the carboxylic acid. Take those out, and then you play squeeze play. Squeaky, and it comes together, and you get this here. That's your ester. That's how esters are made. That process is called esterification. So what you'll notice is this part here, guys, look, write this down, carboxylic acid. That part comes from the carboxylic acid, okay? This part here comes from the alcohol, okay? And as a product, of course, you'll get water as well. So that H and OH will come off, they'll join together to give you water. The rest squeeze together, okay, and gives you what we call an ester, okay? Yep. This, we'll get to the reaction in a bit here, so just know that this part comes off right now, and then it squeezes together. It is made up of 2 parts, alcohol and a carboxylic acid, okay? To name those esters is what all we have to do today, so you don't have to worry about that. But to name esters, you have to have basically 2 parts to it. The alcohol part, is named as an alkyl group, okay? Alcohol part named as an alkyl group. So that part we'll name kind of like an alkyl group. The other part, the carboxylic acid part, the acid part here, okay, is going to be named, well, such as so. We're going to drop the oic acid because that would refer to a carboxylic acid. We're not doing carboxylic acids. It's made up of a carboxylic acid, and we're going to replace the ending with an O8 part instead, okay? This is the only one where you should have a space between them, okay? So you will have a space between different parts here. The alcohol comes first, always, and then the carboxylic acid part comes next, okay? And you're going to have a space between the 2. And in fact, we can maybe write that down. So the alcohol part will come first, space, and then the carboxylic acid, or anything belonging to that carboxylic acid, will come second. Now I can't call it alcohol carboxylic acid because, you know, that's not how we name these. We have to, this is an ester, so it has the O8 ending. That's how we know it's an ester. All right, so let's take a look at some here. Ethyl butanoate. Once again, always, this part here, you'll notice there's a space there. This part is the alcohol, okay? So ethyl is part of the alcohol. The butanoate is from the carboxylic acid part. So here's what you do. Once again, if it was up to me, I'd probably start here first, as always. Butanoate, right away, I know it's an ester because it's got the O8 ending. And butanoate looks like this. 4 carbons, double bond O. Okay? Butanoate comes from butanoic acid, by the way. 4 carbons, O8. Okay? I don't call it butanoic acid because I'm not putting an H here. That's butanoic acid. Okay? I have butanoate, so I need O there. On the other side is what is the alcohol part. And I said it was, what was it, ethyl? Ethyl has 2 carbons, so CH2, CH3. It's an alkyl group, right? Ethyl looks like that, CH2, CH3, right? As from before. So that is ethyl butanoate, and I need to fill in the rest with H's here, of course, guys. Okay? So there's ethyl butanoate. Okay? Questions, anyone? What's the next one here? Where's my list here? Okay. Good. Next one is what? Propyl. Then you'll see a space there. 2-methylpentanoate. I always start at the end. Pentanoate. Pentanoate tells me that is pentanoate. Okay? 5 carbons, double bond O. On the second one, I have a methyl. Notice that's all one word there, guys. 2-methylpentanoate. 1 carbon, 2 carbon right there. Okay? 2-methylpentanoate. There's a propyl and then a space. That's my alcohol part. That propyl is this part over here. CH2, CH2, and a CH3. Okay? That's what goes on the right-hand side there. Fill in the rest with H's, of course. And then we're good to go. Okay? So that's propyl, right-hand side. That comes from the alcohol. 2-methylpentanoate. All right? Good? All right. Next one. Once again, start at the ending. Ethanoate. So ethanoate looks like that. 2 carbons, 2 carbons. Ethanoate, double bond O. On the other side, there's a space there, guys. So I know that between the 1-methylpropyl, there's a space. So I know that 1-methylpropyl is on this side. Propyl is that. Okay, remember you kind of start at the end, right? Work kind of backwards. That's propyl. 1 has a methyl on it. This is carbon 1 here. Okay, remember you start 1 here, 1 there, right? So 1-methyl. Let me put the numbers in here. So that's a 1 there, that's your 1 there. Okay? Yep.
Does it have to be 1 on that side, or
This, you mean the methyl?
yeah, like, does that be on the right or the left, or does it have to be on the left?
It has to be here. That's 1 carbon. It can't be here because that'd be 3 carbon.
Okay,
Yeah.
so
No. Okay. Fill in the rest with H's, of course, guys. So 3, H, H2, H3. Okay. Name them. Okay. Now, naming them sometimes is a little bit tricky because ideally I'd like if they were all kind of like this one here, where, you know, once again, here's the kind of, well, that part there, right? That's the carboxylic part. So that's the part that has to come last, right? That comes from the carboxylic acid part. That part comes last. This part, when it's bonded to the O, this part here is the alkyl group or the alcohol part of this. So I'm going to name this part first, of course, right here. That's 2 carbons. That's ethyl. You're going to leave a space. Okay, so that would be actually ethanol, by the way, is what that would come from. You would use ethanol, and this one here would be 1, 2, 3 carbons. So that's prop, and because the double bond O is in the middle there, that's propanoate. Okay, is how you name esters. I can tell you that to make this reaction, eventually I'm going to ask you this too, and they can get quite complicated, and it really depends on, you can make them so that they can join in different spots, and it can be a nightmare. But I can tell you right now that this was probably made from, eventually, you'll tell me when we get to the reaction part, the esterification part, you'll tell me this is made from ethanol and propanoic acid, are the two here. They can get, and you might say, well, that's pretty easy, and it is, but they can get pretty tough too. Okay, this one here, once again, okay, let's see. Here's my double bond O here. This is my alcohol there, right? Or what it came from the alcohol. So That, well, actually, technically, this part came from the alcohol, but whatever, okay? So that's going to be the first part I write down. That is the methyl part. So I would say methyl here. Now, longest carbon chain containing the C double bond O kind of thing, well, that's this one right here. Right? And I mean, they're not all going to be ranged left to right like you would like them. That's the thing. They're going to get crazy, okay? So you have to kind of keep in mind where the double bond O is, what do you have on both sides. This is 1, 2, 3, 4, 5, so that is pent, right? It is an ester, so it's pentanoate. I'm going to put that over here somewhere, pentanoate. But I also, don't forget, have to describe this group right here that's on that pentanoate part. So that is on the second carbon. 1, 2 is an ethyl group. So right here I'm going to put 2-ethyl pentanoate. That's all one word. This is your space right there. Okay? The alcohol part is separate from the, well, carboxylic acid part. Yes? Okay? Like I said, these can get pretty confusing. If you're going to make those two, it's not as simple anymore. Okay? Because you have to make sure it attaches to the right spot here, basically, and so on. But we'll get into that. Yeah. Yeah, the one attached to the O is the alcohol part. Well, that came from the alcohol. And then, of course, that's going to be discussed as an add-on group. The rest comes from the carboxylic acid. Okay? All right? Okay? Is that it? Oh, no. Physical properties of esters. You don't have a OH anymore, so you don't have that hydrogen bonding anymore. If you look back at the drawings here, look, there's no OH here anymore. So no more hydrogen bonding. It's still polar, yes. Kind of the same rules apply, but because there's no OH, there's no hydrogen bonding. You know, as far as a similar ester to a similar carboxylic acid, the carboxylic acid would probably have a higher melting boiling point because it has hydrogen bonding, OH. This ester does not have OH, so probably not quite as high. Okay, ester molecules cannot form hydrogen bonds. Boiling points tend to be much lower than similar sized alcohols and carboxylic acids, so they kind of rank a little bit lower. Yep. Yes, they would be higher than alkanes. Yeah, because they are polar. Alkanes tend to be nonpolar. Just wait, I got some questions for you. And you know, most noticeable property of esters is their distinctive scents, and there's 2 of them there for you.